Welcome learners. In today's lecture, we are going to look into the concept of mutual inductance. We are going to see what happens when we bring one storage element, in this case an inductor, in close vicinity to another passive element which is the same inductor. We are going to first learn about the concept of self-inductance. This is something that we have already talked about when we were discussing the working principle of an inductor represented by symbol L having the units of Henry. And after that, we are going to talk about the main content for today's discussion, that is on mutual inductance. So before we begin, we just revisit what we had studied last time in the sense that what was an inductor. So the basic idea behind the inductor was that if we take any simple wire having terminals A and B, and we know that this simple wire is sometimes called as a short circuited wire. So it's a short circuit wire, meaning that the current can easily flow through it, ideally in amperes at infinite amount, but the voltage appearing is 0 volts. If we consider the resistance to be 0, then as per Ohm's law, the voltage comes out to be 0 in a short circuited wire. Now if we take this wire and we wrap it around any core material, that core material, let's say, can be a cylindrical one, it can be rectangular, or it can be cylindrical or a square. So if we take this wire and wrap it around any core material, the core being this cylinder, so this is your core material, that can be sometimes of magnetic nature, sometimes non-magnetic. So if we wrap it around this coil, this wire around this cylindrical core, what we get is a coil-like structure, and we say that we have transformed our simple wire to nothing but a new element known as inductor. And then the basic governing principle or the working principle of an inductor follows the guidelines provided to us by Ampere's law and Faraday's law, where Faraday finalized this equation saying that if any current flows through this conductive material which is made up of copper or aluminum or gold, and what we are calling it as a coil, so if current I of t, so the current which is changing with respect to time, if it flows through this coil which is made of a conducting material, magnetic field is going to be produced around these coils or these segments of the coil. So we can say, or Faraday's related, that the voltage which is going to produce as an effect of these magnetic fields, induced voltage, is directly proportional to the rate of change of current, or the equation becomes V equals to L di by dt, and this is the basic governing equation for inductor if we need to find the voltage. Similarly, the current can be figured out if we find the integral of the same equation number 1. So this procedure also led us to this understanding of the concept of self-inductance. So now what happens if we take this coil, and let me draw it over here in a broader manner. So it has terminals A and B, and we know if the current flows through this, a time changing current I of t, the coil is going to produce magnetic field around each segment of the coil. So if we take it parts by parts, we know that a magnetic field is going to be produced around this section of the coil, then it is going to be produced in this section, in this section, in this section, in this section, and so on and so forth. Normally, as we studied in our initial lectures, that whenever we talk about circuit elements, we consider not the portions inside the element, rather we consider them to be lumped elements. So by lumped elements, we mean that instantaneously the same effect is observed from point A to point B. So this is what we called as lumped behavior. So rather that we have a single analysis of each magnetic field inside each turn of the coil, we consider that the effect is instantaneously spread over all of the inductor. So we say that whenever a changing current I of t is moving through a conductor, it is going to produce a magnetic field. But if you look back into each segments, Faraday also proposed that each magnetic field in this segment is now producing an induced voltage on it. So this portion will have an induced voltage of V, then this coil will have another induced voltage, this will have another, and so on and so forth. So this process where the flow of current produces magnetic field and the same magnetic field produces an induced voltage in the single inductor, this is known as self-inductance. This phenomena is known as self-inductance. So to summarize, if we have a simple inductor which is represented in this symbol for the electrical analysis, if a current moves through it, a magnetic field is produced and the same magnetic field is going to induce an EMF or voltage across this, and this process for a single inductor is known as self-inductance. Now let us come to our today's topic of discussion, which is mutual inductance. So now what is this mutual inductance that we want to talk about? So mutual inductance happens if you take one coil, let's say the inductor shown onto your left. So let me call this as circuit number 1. This portion to be, or this section of the complete circuit to be circuit 1. The other is called circuit number 2. So let us first look into the first circuit onto your left and see what is happening. So we can see that we have an inductor L1 supported by a resistor to control the flow of current I1, and we have a voltage source V of G in the left side of the circuit. Now on the right hand side we have another inductor represented by L2, and we have placed a resistor again to control the flow of current, and the current on the right hand side is I2, left hand side has the current I1. So now what happens is that if we talk about circuit 1, we know that this current I1, which is generated or originated from the source, is basically going to flow through the resistor and it is going to enter inside this inductor. So we have represented this by L1, and we know that when the current I1 flows through this inductor, magnetic field is going to be produced, and the same way induced EMF is also going to be introduced inside this one. So we say that L1 is a self-inducting inductor. So this is why we label it as L1. The same thing can be said about L2. If this current I2 flows through this followed by this resistor, so we can say that L2 is represented as a self-inductance, or the inductor that is capable of self-inducing the induced EMF onto this. So these are L1 and L2, and now in this scenario what is happening is that we have a main circuit, circuit number 1, consisting of L1, and we have brought in close vicinity to circuit number 1 the circuit number 2, which is having the inductor L2. So now we want to see what is going to happen in terms of the magnetic field which is produced by L1. So what happens is that the magnetic field produced by L1 is going to interact with the new inductor L2, which is brought in close vicinity to the circuit number 1. Now since the magnetic field has been introduced to the second inductor L2, we know that induced voltage is going to be produced inside L2, and this is the same thing which Faraday's law is talking about. So whenever we have a time changing magnetic field, an induced voltage is going to produce. So we can say that R2 is going to have voltage V2, which is the induced EMF or the induced voltage produced because of the magnetic field coupling from L1 to L2, and thus this coupling is known as mutual inductance, represented by symbol N and the arrowheads representing that the mutual effect or the magnetic effect is happening between inductor 1 and inductor 2. So in our scenario, M is representing the mutual inductance, which means the effect is observed by L2 due to L1, and similarly L1 is experiencing the same magnetic effect produced by L2. So this is how the mutual inductance basically works. So now let us further see what we can understand in terms of mutual inductances. So whenever we are given such kind of circuits, we need to design certain steps and then we analyze our circuits based on that. So what are the steps associated with this? So let us say we follow these steps when we want to electrically analyze this circuit. So the first step is that we select the reference current direction. So the direction can be clockwise or counterclockwise as shown here with I1 and I2. So you can see I1 is in the clockwise direction and I2 is in the counterclockwise direction. The second step will be that we need to sum all the voltages inside these two loops, which means we have to apply the Kirchhoff's voltage law. And the third one is we need to figure out the polarities, or you can say the addition and subtraction sign for mutual inductance M in the equation. So we need to now know what is going to be the sign for M when we are trying to solve the KVL, let's say in loop number 1 represented by I1 and loop number 2 represented by I2. So these are the three steps that we always follow whenever analyzing a mutual inductance based circuit provided to us. So let us see how can we apply these steps to a simple scenario shown over here. So let us say this is our case number 1. Obviously, why there are different cases, we are going to look into this, but let us first see what we can extract from this kind of figure that has been shown to us. So in this case number 1, we can see again we have two circuits side by side. So this is my circuit number 1, or some portion or segment of the original circuit. So I have labeled it as circuit 1 on our left and circuit 2 on our right. So let us first see where is the reference direction. Here we can see that I1 is moving in this direction, so it means that the direction or the flow of current was such in the clockwise. So I can say this is my I1. On the circuit 2, the current is moving in the opposite side, so the flow of the direction or for the loop current was I2. So we have defined the first point in figuring out the reference direction for the currents. The second step is we need to sum all the voltages, which means apply KVL. So let us talk about loop 1 onto our left. So what we normally do when we apply KVL, first we need to identify what is going to be the positive and negative sign for the voltages. Let us say if we follow the convention from the book that whenever the movement of the current is from negative to positive, which we called as a voltage rise, we are going to take the sign to be a negative one, and whenever there is a voltage drop from positive to negative, we are going to take the sign to be positive. So now let us apply this analogy. So this in the first circuit or loop 1, we can say if we start from this node, we see the first thing we encounter in the flow of current is the minus voltage sign, or this is the voltage source or the generated voltage V of G. Then the current enters resistor. We by default know the current entering is through the positive terminal and leaves through the negative terminal. So we can write it as plus the voltage appearing across resistor 1. Then we are going to look into the inductor, the current flowing inside the inductor. We already know it is positive and negative. So we are going to write it as voltage across L1. But now we need to consider what is the value of M. So we are going to write M, or we can say what is the voltage with regards to M, and whole equation equals to 0. But we still need to figure out what is going to be the sign over here, whether it is negative or is it positive. We don't know this yet. So how can we figure out the effect of mutual coupling coming from L2 in the form of M on L1? So how can we figure this out? In order to figure this out, we use something known as dot convention. So this is what we are talking about. Now what is a dot convention? So dot convention says that whenever the reference direction of the current enters or leaves, so we talk about, let's say first, if it is entering the dotted terminal of a coil, the reference polarity of the voltage on the other coil or the dot on the other coil is taken as positive, and if the current leaves, the dot polarity on the other coil is taken as negative. So now what does it mean? So let us understand this. So again, the idea behind dot convention is that we need to figure out what is going to be the sign associated over here with this voltage at mutual coupling? We don't know the sign with this. So in order to find this, we follow the dot convention. So let us see what we are going to find. So let us say we basically have these dots represented in our circuit. So one case, so case number one is that the dots are presented over here. So let me highlight this. So this is the first dot that we have placed on the left side or the circuit number 1, which is at the terminal of the inductor L1, and the next dot is appearing in circuit number 2 with the terminal of second inductor L2. So now we need to see what is the flow of current inside this these dots. So since we are talking about the effect of M2 to the first inductor, we have to see the flow of current that is with regards to this dot. So we can see that I2 is basically leaving the dot and then moving outward. So since the current is leaving from here, the polarity for M is going to be negative. So let me use another color to make it more easy. So since the current in the second loop is leaving, so the polarity on the first side will be negative for M, and obviously the opposite side will be positive. So this is going to be my M di2 by dt. Similarly, if the current was entering this terminal, then the polarity would have been changed to positive and negative. So since now the current is leaving, so we are taking the polarity on the first side to be negative, and obviously the other side will be positive. So we can say that the effect of M2 on inductor L1 is going to be what? It is going to be negative. So this is what we are going to have. So if we complete this equation, what is the equation going to be? So it is going to be minus Vg plus I1 R1, and what is the voltage across the inductor? It is L1, the rate of change of the first current inside L1, minus what is the voltage with regards to the magnetic coupling? So it is going to be M, and the effect is coming from the second loop, which is I2 d2 equals to 0. So this is the equation which I got for my first loop. Again, the important point being how to use dot convention to figure out the sign of M. Now let us write the equation for loop number 2. So this was for the first loop. Now what about the second loop? So let's apply KVL to loop number 2. So if we look at loop number 2 here, the current is flowing in the counterclockwise direction. I can take any point. Let us say if I start from this node, so this is positive, this is negative, and then we have the current which is entering. So I can say positive, negative, and then we see. So obviously there is no voltage source, so I can write 0 equals to I2 R2. Then the inductor is going to be plus L2 di2 by dt, rate of change of current because of the second, and then we need to write the magnetic field effect coming from the first inductor. So it is going to be di1 by dt. Now we need to know what is going to be the sign associated with M. So in order to find the sign which is coming from the first current, we need to look at the flow of current in the first loop, and we see that the current is first entering the positive terminal, which means, so I1 is basically entering the positive terminal, which means the polarities of the dot on the second coil is going to be plus here and obviously negative here. So M is going to be di1 by dt. So here the sign is going to be such, so when I move from the counterclockwise direction, the first thing I'm going to encounter for M is negative M di1 by dt. So this is my equation number 2 for the second loop, and the above equation was for equation number 1. So this is how you basically find the equation or sum of all voltages, especially for the mutual inductance effect on both of the inductors. So similarly, so we have figured out how to find the polarities, and this is through the dot convention, the third step that we have shown over here. Let us look into more scenarios of writing the equations. So we have seen the first scenario where the dot convention was having a dot in the diagonal or opposite side. Now let us take the second case. So let us take case number 2 to understand the dot convention and writing the equation. So the second case, let us draw the inductor as such. So this is the voltage applied, and obviously the induced voltage is going to produce on the other side after the magnetic coupling. So in previous scenario we had the dot convention to be on the top and bottom. Now we can replace the dots. So let me use another color for that. So let us replace the dots. So the first mutual coupling dot is at this side and the other is on the top side. Now we have changed the order, and let us see what is going to happen in the second case. So the mutual coupling is basically happening. So let us represent it by M. This is the inductance L1. This is the inductance L2 for the second portion or second side. Again, we remember that L1 and L2 are self inductances, and M is the mutual inductance. So the first step is obviously to define the reference direction for the current if we follow this step. The second is then we sum the voltages, and third we associate the polarities for the mutual inductance. So if we start with the first step, we need to define the reference direction. So let us say I am taking the direction clockwise for the first current I1, and on the other side I am taking in the counterclockwise for I2. So now let us write the equation for loop 1, or the KVL equation for loop 1. This is KVL to sum of all the voltages. Let us start from this node. So it is going to be minus V1, then plus, because the current is entering over here, so the voltage across the inductor will be L1 di1 by dt. Now I want to know what is the polarity for the mutual inductance effect, which is coming from L2 into L1. So I know that I'm going to write the mutual effect coming from the second side. So I'm writing d by dt for I2. This all equals to 0. But what is going to be the sign? So in order to find the sign, I'm going to look into the current in the second circuit. So this is my circuit number 2, again for reference. This is my circuit number 1. So in circuit number 2, I see that current is basically entering into this position. So here the current is entering into this position. So I can say if the current is entering, my polarity here will be plus, and here it is going to be negative. So my equation will come out to be negative M di2 by dt, and this is my equation over here. Again, to highlight, these are my terminals. So these are my dot conventions over here. So now let us write equation for the second loop. So loop number 2. So KVL obviously. So now let us look at the circuit on the right side. So let us start from anywhere. This is my, let's say, node. So equation will be minus V2. We know the current enters from the positive, leaves from the negative. So it is going to be plus L2 di2 by dt. And now I am going to write the mutual effect coming from L1 into L2. So it is going to be M di1 by dt equals to 0. Now again, what is going to be the sign for this M? So we have to look into the current one, I1. So I1 is basically leaving this current, leaving the dotted terminal. So if it is leaving the dotted terminal, it means I will have the M sign of negative over here and positive on the other side. So I2, I'm seeing that my current is entering first M, so it is going to be negative side of the equation. So this is my loop 2's equation, and this is the second case which we have studied. So now let us talk about two more cases. So this was the second case, and you can see that the equations for this scenario, case number 2, equals to, so the equations for this is equal to the case number 1 equations when the dotted terminals are opposite to each other or in a diagonal position. So equation we can see for loop 1 and loop 2 is should be the same as that for 1. So if we go to the first equation, it is minus Vg I1 R1, L1 is a positive sign, so we can say minus voltage then inductor is positive and mutual inductance is negative. So we can also see that voltage is negative, inductance is positive, and mutual inductance is negative. Similarly, for the second, voltage is negative, inductance is positive, mutual inductance is negative. The same should go for the second case, where mutual inductance is negative, inductance is positive, and then we have no voltage source, because in this we haven't basically put any voltage source over here. But again, if there was a source, it would have been a positive value. So case number 1 has the same equations or output equations for the loops as equal to case number 2. Now let us write two more cases where the dot conventions are side by side to each other. So this is case number 3. So case number 3 is, let us draw this. So this is inductor, this is another inductor. Again, it has certain voltage applied, and the opposite side has an induced voltage called V2. And let us also prepare the fourth case. This is case number 4. So this is the inductor for this side, and this is the inductor for the other side. This is voltage V1, and the voltage produced on the other side is V2. Let us populate this with respective values. So let us say this is for case 3, this is L1, L2, again L1 and L2. Both of them are having mutual coupling represented by this M and the arrow signs for both of the sides. Now let us assume this is subsection circuit 1, circuit 2. This is subsection circuit 1 and circuit 2. Now we want to put the dot convention. So now let us go side by side. So first dot is over here at the terminal of L1, and the other is side by side on top of L2. And then we have in case number 4 side by side, but this time around the dotted terminals are on the bottom. So now let us go step by step. First start with case number 3 and see what we have to do. We have to basically first decide the reference direction of the current. So this is my current I1 in the clockwise direction. This is I2 in the counterclockwise direction. Same can be said for case number 4 in terms of I1 and in terms of I2. So now let us focus to case number 3 and let us write the equation for loop number 1. So for loop number 1, we start from, let's say, the bottom side as we did for the previous case. So it is going to be minus V1 plus L, because the current is entering, so the polarities will be such for all the inductors. Let us populate that. So it is going to be L di1 by dt. This is L1. Now the next will be the mutual coupling effect from the second circuit. So I am writing di2 by dt equals to 0. Now what is going to be the sign for this? So in order to find the sign for this, we have to look at the flow of current in the second circuit scenario. We can see that current is basically entering the terminal. So it is entering the terminal. So I can say that the polarity for my case is going to be positive over here and negative over here for mutual inductance. So the sign is, now when I follow the loop I1, I see the first thing I encounter for mutual inductance is the positive sign. So this is going to be plus M di2 by dt. Now let us write the equation for loop 2. So for loop 2, again we start from the bottom side. We can write minus V2. Inductor will have plus L2 di2 by dt. Then we have to write the equation for mutual inductance. It is the effect coming from the first circuit. So I am writing di1 by dt equals to 0. What is going to be the sign? In this case, again we have to look at the current flow. We see that the current first enters the terminal and then it leaves. So it's again going to be positive sign over here and negative sign over here. So the mutual couplings will be plus M di1 by dt. So this is how we write the equation for the third case. And since we know by observation that whenever dotted terminals are diagonal, their cases have the same equation as we saw with case 1 and case 2. Similarly, case 3 and case 4 have the same dotted terminals, which means they are side to side. So it doesn't matter if they are on the top, if I can just highlight it. So in case number 3, the dotted terminals were side by side, or we say they are parallel to each other. In case number 4, again the dotted terminals are side to side or parallel to each other, but they are on the bottom side. So which means by observation of the diagonal case previously, the equations for the both loops should be the same. So for loop 1, our equation will be same as that of case number 3. It should be minus V1 plus L1 di1 by dt plus m di2 by dt equals to 0. Similarly, for loop number 2, you should get the same equation V2L di2 by dt plus m di1 by dt equals to 0. And you can verify by solving this again, but case number 3 and case number 4 will have the same set of equations, and case number 2 and case number 1 will have the same set of equations. So this is how we deal with mutual coupling between two inductors, in which the magnetic fields basically create the mutual inductance. So now let us talk about what happens if these elements are connected in series or parallel. So let us say that now the inductances are connected in series. So if we have series combination, so how many ways we can write the equation? So series combination in terms of mutual inductance. Similarly, we'll go for parallel combination as well. So series combination in terms of mutual inductance. So we know the first need for these combinations is that whenever we want to perform any physical experiment and we don't have the exact values for inductors, so we can combine them in such a way to get an equivalent inductance. And also let us see what we can do. So the idea is that if we have, let's say, a set of inductors, let's say inductor L1, inductor L2, and it is let me draw this again. So let us say I have this circuit, inductor L1 followed by another inductor, and then we have a power supply to this. So this is voltage, and this is inductor L1, this is inductor L2. But now the idea is we want to create an equivalent inductance, but the concept of mutual inductance is over here, which means that our system is now going to have a mutual inductance M between these two inductors, and which means we need to know where the dot convention is. So let us say in the first case, let us call this case number 1, we placed the dots at the input of the terminals. So L1 dot is over here and L2's dot is at the input side, and now we want to figure out the L equivalent available for this kind of a circuit. So in order to do this, we know that whenever a current is flowing, so basically we first figure out, or we follow the steps. The first step being define the reference current direction. The second step, sum the voltages, which means apply KVL. Sum the voltages, which means use KVL. And finally, you find the polarity or polarities for the mutual inductance M. Okay, so let us keep it simple. We apply the current's direction to be in the clockwise, so let me call this I1. And I can start from any voltage I want. I can start from this node position and do the analysis for this KVL. So once we start from this node, let us call this node A, we know that the voltage is going to generate a current I of t. If this is an AC source, it can, since it's DC source, so I can say just a definite value of current. So the current will start to move. It will reach this point. Now we know that when the current enters the inductor, by default we say it's a positive sign followed by negative sign. The same currents then enter inductor 2 with the positive side and negative side on its leaving terminal, and then the current reaches back to its intended point. So now how can we write the KVL equation? Before we write the KVL equation, we need to know the polarities for the mutual inductance. So let us write the polarities for the mutual inductance. How we can find this? So we need to know the direction of current. So if I want to know the value of M appearing for L1, so if I want to know what is going to be M with respect to the I2 by IT, so I need to know what is the current entering over the second terminal. So the current is basically first entering the dotted terminal, which means that my polarity for the dot convention around L1 is going to be positive and the other side will be negative. Similarly, when I will reach the equation for L2, I need to know the magnetic field's polarity for the current effect on L2 from L1 or the current I1. So here for the right hand magnetic field, I need to know what was the current entering in the first side, and again the current I1 was first entering the dotted terminal, so again the polarities will be plus and minus for the mutual inductance. So here I can write the equation as, so let us use this area to write the equation as L1 di1 by dt, then plus m di2 by dt, then I'll have plus L2 di2 by dt, then I'm going to have plus m di1 by dt, and then minus v equals to 0. Now we know that the current remains the same in a series circuit, so I don't need to write di1, di2, di and so on. I can just write to be a simple current, and then the equation simplifies to voltage equals to di by dt, and I'll be left with L1 plus L2 plus 2m, and this portion here is basically the L equivalent that we want to know. So this is the L equivalent. So L equivalent comes out to be L1 plus L2 plus 2m. So this whole circuit can be represented by a single L equivalent element where the effect of coupling is shown. So this is how we can simplify this series combination into a simple L equivalent circuit, and the mathematical expression for this is represented over here. So this is the L equivalent that we can use when we are dealing with mutual coupling. Now let us talk about the second case. So case number 2. In case number 2, we are going to rearrange the dot conventions. So in the first scenario, I am going to highlight this so it becomes easy. In the first case, these were the dots or dot conventions that we used, which means that they were at the input of the inductors. Now in the second scenario, in case number 2, let us again draw the inductors with any voltage source, plus minus, this is L1, this is L2, and now let us see where the dots are going to be placed. So I'm going to use the same color combination because we want to have mutual coupling between these two inductors represented by M. So now the dots are placed at the exits of the terminal for both the inductors. So these are the dot conventions. These are basically going to help us see the flow of current. So if I want to know the flow of current, again I'm going to write it in the term of so the first step is to consider the clockwise current. I'm taking the clockwise current, but you have the liberty to do the counterclockwise as well. So now the clockwise is decided. I know the current is going to move from here, it is going to reach here. Then for the inductor, the value will be plus and negative, plus and negative. Now let's talk about the equation. So the equation comes out to be, so equation for this comes out to be, if I take this node as my starting point, so it is going to be plus L di by dt. Again the current remains the same, so I'm just taking di by dt. Now what about M di by dt, the effect coming from L2 into L1? So we have to see where is the current, when what happens to the current when it reaches. So once the current passes through L1, it reaches at this point. So this was current over here. Now it is entering the inductor, but here it is leaving the dotted terminal. Since it is leaving the dotted terminal, which means the polarity for M will be negative over here and positive on the other side. So I can write my equation when the current is, it's going to be plus M1 M di by dt. Then we come to the second inductor. So this is L1, this is now L2 di by dt, and then I need to write the equation for M di by dt. So this is the effect of M on L2 through L1. So the current, I will look the current I entering L1, and we see that the current is leaving the dotted terminal over here. This means the polarity here will be negative and here it will be positive for M. So the equation again becomes +1. So finally, and obviously this equals to voltage V. So then equation V equals to, if I take the current to be common, di by dt, I get the same effect of L1 L2 plus 2M, and this portion is again my L equivalent. So we see again that if the dotted terminals are behaving in such a way that either both of them are at the input of the terminals, so the equation becomes this one as we saw with case 1, or if both the dotted terminals are on the exit side of the inductor terminals, we get the same equation over here. So this means that case number 1 and case number 2 are having the same set of equations. So I can summarize that again in this case 1 is having the same equations as case 2. So this is the observation which we already saw in the simple analysis of mutual inductance, and it is also happening the same way when we are considering a serial combination of inductance. So let us continue our discussion and move to the third and fourth case. So case number 3, and let us write case number 4 here as well. So case number 3 is, now we are going to rearrange the inductors. Position will remain in the same way, but the dot convention symbols are going to change. So let me draw them side by side. So this is the voltage on both the cases. This is inductor L1, L2, L1, L2. So what we normally do is we take this as our node. You can take any position to start the KVL. We apply the mutual coupling symbol. The symbol is very important because it lets the user know that these elements are coupling with each other. We apply the flow of current in the clockwise direction, I of t. Now what we are going to do this time, we are going to change the position of dot conventions. In the first case, now we are going to place the dot convention at the input side of the terminal, and for the other case it is the leaving the terminal. And in the case 4 we said that first it is leaving and on the other side it is entering the terminal. So let me highlight this for easy visibility. So these are the conventions. Now we can see that for one side it is entering, for the other side it is leaving, and vice versa for case number 4. So now let us start writing the equation for these two cases. So here the equation for case 3 comes out to be, if we start from node A, so the first thing we encounter, so this is the current I which is generated, this is the current I here, this is the current I. Same goes for case number 4 because it is going to help us. So equation will be L1 di by dt. Now the effect of mutual inductance coming from L2 into L1. So we need to know what is the current moving in L2. So we know that current is leaving, so this becomes negative and this side becomes positive. So it is going to be negative M di by dt plus L2 di by dt. Again we need to write for inductance minus V equals to 0. So now we need to know the effect coming from L1 into L2, which means we need to know the current I entering. So here we can see it is entering, so this side becomes positive and the other side becomes negative. So the equation will be negative di by dt. So if we simplify the equation, so voltage equals to and if we take the common variables out, so it is L1 plus L2 minus 2M, and the current is di by dt. So we can see that the L equivalent in this case comes out to be this portion, which is now with a negative sign. In the previous case it was a positive sign, now it's a negative sign. And with our observation we know that since case 1 and case 2 were the same results, case 3 and case 4 is also going to produce the same result. So the equation over here will also be L1 plus L2 minus 2M with the common current between them. So this is the L equivalent that we are interested in. So these are the 4 cases when we are dealing with inductors to be in a serial connection. And now let us move to the combination where the inductors are connected in parallel and the mutual couplings or mutual inductance is basically happening between them. So now let us talk about parallel combination in the context of mutual inductance. Okay. So let us again start with 4 cases. The first case, so the first case is such, and we can go side by side if that's okay. The second case, let me draw it over here, so to save time. So in the first case, the circuit might look like this. This is inductor 1 and this is another inductor, and we can say the voltage applied over here is V. This is L1, this is L2, and we basically need to know the mutual coupling happening between these two inductors, so represented by M. Now let us introduce the mutual or dot convention. So the first is basically at the input for both of the inductors. So these are the dots that we have, and we want to know what is going to be the scenario. Same circuit can be drawn for the second case. You have inductor 1 and you have inductor 2. Again, it will have a certain voltage with L1, L2. The mutual coupling or mutual inductance is happening with regards to this sign, but this time instead of side by side on the top position, they are side by side on the bottom end of the inductor. So this is the mutual inductance or the dot terminal convention we have. So let us highlight this by this color. So now let us do the analysis. Okay, so now we want to know what is going to happen. Let us study case number 1. So in case number 1, we need to first identify the direction of the current. So let us say this is in this way, clockwise, and obviously the second loop is this way. Let me call this I1 and I2. Same goes for I1 and I2. So let us focus on the first case to your left. So how can we go about this? So we can apply the KVL on loop 1 or loop 1. So if we apply KVL on loop 1, what is the equation that we are getting? Obviously we want to write the equation in terms of the voltages. So we can write, if I start from this point, so we know that voltage is equal to, the first thing we encounter in terms of the flow of current for the inductor is that the direction of the inductor polarities or the current are in the downward direction, so from positive to negative, and same will go for the other side as well. So for loop 1, I can write the equation for inductor to be L1 d by dt, but now the current is between two branches, so I can write it as I1 minus I2. This is going to be the inductor. Now I want to know what is the equation for M, because this M is coming from the second current, so it is going to be di2 by dt. This is the value that I am going to have. Now what is going to be the sign for M? Again we have to look the current I2 and see whether it is leaving or entering. So we can see that this current is basically leaving the circuit. So we can say that this is so we have to look at the current M2, or for the M. So in order to find the sign for M, we have to look for the current I2, and we know that I2 is in this loop and this is the terminal. So the current basically entered and then it left. So when it is entering, so the sign becomes positive at this dot and negative at this dot for m. So I can say that it is going to be plus m di2 by dt. So this is my first equation. I can further simplify this equation. I can write it as L1 di1 by dt. Since di2 and I2 are the same, I can take m minus L di2 by dt. So this is my equation for the first loop. Let me call this one. Now let us write the equation for the second loop. So loop 2. So loop 2, what is going to be for loop 2? So let us say for loop 2 there is no voltage source, so I can directly write 0 equals to, now so I'm starting from this node, okay. So for inductor I will have plus L2 di2 by dt. Now I want to know what is the effect of mutual coupling M coming from the first inductor. So I want to know what is the sign for M over here. So the sign for M over here depends upon the flow of current in the first loop L1. So I can see that current is entering this dotted terminal and then it is leaving. So the sign will be plus and negative. So it is going to be plus M, but the thing to note is that is going to be di by dt, but the difference is that the current flowing through here is the difference of two currents, so it is going to be I1 minus I2. So this is basically the thing that is of importance, that we want to know the effect of M over here with regards to current I1. So current I1 is a current going through branch L1 which is between two loops. So here the current will be di1 minus I2 by IT. Then now I have started from here, I have moved, and now I'm going to enter over here. Here the first thing I encounter is negative M di1 by dt. So this is basically di2 because it was the effect coming from there, di2 by dt. And then the next element after this is going to be plus, since I am going in the current is in the opposite direction, L1 d by dt. Again the inductor is I2 minus I1. So this is the equation that I am going to have. So this is the equation for the second loop. So I can write it as equation number 2. So now if you do some simplification, which I can share with you at the end of this presentation via a snapshot, you should get the final equation for this loop to be, so what basically we are going to do is we are going to take d2 to be common and replace its value in equation number 2. From equation number 2 then you can figure out the value of di2 by dt. Once you simplify this, the L equivalent should come out to be L1 L2 minus m square divided by L1 plus L2 minus 2m. So this is the L equivalent when we have a parallel combination. Again, as I mentioned, I can share with you at the end of this lecture a snapshot where these equation 1 and 2s are simplified to get this L equivalent over here. And once we have this equation, we know that what happens with case 2, it is going to have the same behavior. So case 2 is going to have the same set of equations for L equivalent because both of these dot conventions are side by side as they were over here, only they have been moved from top to bottom. Similarly, for case 3 and case 4, we don't need to prove anything. From our observation, we know that if this is case 3 being such that now the dot terminals are, so this is L1, this is L2, and this is case 4 where the inductors are placed as such, this is L1 and L2. So the dot terminals are basically going to be changed, so one will be on the top and other will be on the bottom. Similarly, one can be on the bottom and the other will be on the top. So the equation comes out to be that case 3 equals to case 4. I am just going to write the equation from our prior experiences, that it is going to be L1 L2 minus m square divided by L1 plus L2 plus 2m. So you can see there is only a difference of one sign between these two equations when we move from case 1 to case 3 and 4. So this is how the parallel inductance with regards to mutual inductance or combination is solved. The only thing is that how we deal with the dot conventions when the equations are entering or leaving. For your easyability, I can even write the values for inductances. That can be, let's say for case number 2, here we are going to have m di2 by dt, and here the m value is going to be di1 minus I2 by dt, because we are passing the current L1. Similarly, for case number 3, the value of m is equal to di2 by dt, the effect of L2 and L1, and here the effect will be d by dt I1 minus I2. Similarly, here the effect will be m di2 by dt, and here the effect will be m d by dt I1 minus I2. So this is basically the values for these currents and circuits that we just saw. So this is basically I1 and I2. And that concludes our today's lecture. We have seen how to deal with mutual inductances. If I want to summarize today's lecture, we have talked about what is mutual inductance. We started with concept of self-inductance, that how self-inductance happens. Again, we saw from the Ampere's and Faraday's law, especially Faraday's law pointed us to this direction of self-inductance. Then we talked about mutual inductance, what happens when we bring one storage element in proximity to the other. In our example, it is one inductor element in close vicinity to other inductor element L2. So in order to solve this mutual inductances, we basically follow some steps. Those steps being, we need to select the reference direction, then we apply KVL to some of the voltages, and then we figure out the polarities for the mutual inductance, which is represented by M. Then we saw different cases. Case 1 being that how we can identify the value of M with regards to di1 and di2. Then we saw 3 more cases of how the mutual inductance is going to be figured out when the dot convention is changed, when it becomes side to side, when it becomes opposite. Similarly, when we move to series combination of inductances, how the mutual inductances or dot convention is going to give us the equations where the same entry points or same exit points of the dot convention will have the same mathematical expressions as case number 1 and case number 2. And if the dot conventions are changed, like inductor 1 has an entry point as shown over here and the dot convention is at the exit of the other inductor, then the equations will be different. The only difference comes in their sign, which is replaced from positive to negative, but cases remain the same. So case 3 equal to case 4. Same goes with parallel combination. If you have side by side dot conventions, the answer will be the same, where the equation will be L1 L2 m square divided by L1 plus L2 minus 2m, shown over here. And if you change the signs or to change the conventions from side by side into diagonal as shown over here, so let me highlight it over here. So in case number 3 and 4, the dot conventions are now diagonal to each other, so the equation will be the same. The only thing will be negative sign will be changed with the positive one. So that concludes today's lecture.